notice that everything we've done in this unit up to this point has assumed that we have continuous data, continuous variables we're looking at. So we're looking at height, we're looking at weight, we're looking at time, something like that. You may say, well, what if we've got categorical data? We'll talk about that today, but not obviously in all cases. So what we're going to look at is if you have success-failure data. So that means for everything in the population we're looking at, it's success-failure. You have to be able to classify everything as a success or failure. So male, female, what are some of the examples I have? That would be recording gender, right? Will you vote for candidate A or will you vote for candidate B? One of those is success. And remember, we're not passing judgment when we call something a success. We're just, that's literally whatever it is we're interested in or counting or something like that. You know, do you have do the subjects have children or not have children? Success, failure, yes, no. Have been immunized, have not been immunized, owns a car, doesn't own a car, like that. So those are obviously categories. And they're categories with two levels, success and failure. What we're going to look at is proportions. Okay? So we're going to look at proportion of successes. So this is the picture you want to have in your mind. So we've got some sort of a population here. And remember, we're going to assume it's some sort of a large population or a population that's difficult to access. We can't take a census. If we could take a census, we would get success and failure for each thing or item or person in the population, right? So we'd say, oh, person 1, that's a success. Person 2, oh, that's a failure. Success, failure, whatever. So this population is made up of a bunch of successes and failures. The parameter of interest is pi. So the parameter over here that we're trying to estimate or want to know something about is pi. And pi is literally just the proportion of successes in the population. We're going to use the word proportion quite a bit today and over the next bit. When you hear proportion, just think percentage. Right? Percentage is a number out of 100. Proportion is a number out of 1. So, 20% is equivalent to a proportion of 0.2, just moving the decimal place. So how would we calculate pi if we took a census or something like that? Pi would be the number of successes in the population divided by the number in population. Right? So in theory, if we could get a census, we could calculate pi. If you can't read that, it says the number of successes in the population divided by the number in the population. Okay? I didn't leave myself much room to write here. Well, as usual, we say, okay, well, we can't get a census, but what we could do is take a sample, hopefully a simple random sample. At least that's what we're going to look at right now. And so in this sample, we're going to get some successes and failures, right, for each person in the sample. So it might be a natural thing to do to say, all right, well, we're interested in pi, which is the proportion of successes in the population. Maybe what we would want to do is, if we take a simple random sample, maybe we want to look at the proportion of successes in the sample, right? That would be a logical thing to do. And we're going to call that P. So this is pi. P is the sample proportion. Pi is the population proportion, p is the sample proportion.
How about pi was the parameter?
Pi is the parameter.
Oh.
Yeah, when you talk about a population attribute, that's a parameter. So p is the sample proportion, and pi is the population proportion. Yeah, pi is a parameter, and p is a statistic. So you can think about p as an estimate or a point estimate of pi. How would you calculate p? Do you want to guess? Yeah, it'd be just the same as you would for pi, except instead of dealing with the population, you're dealing with the sample. So to calculate p, that's the number of successes in the sample divided by the number in the sample. And I can zoom in on this if you want me to. Can you guys see this any better? Okay, so again, just to kind of review, population is made up of a bunch of successes and failures. There's just a bunch of them there. We can't get a census. If we did get a census, what we would maybe be interested in is pi, where pi is the proportion of successes in the population. So theoretically, if we had a census to calculate pi, it'd be the number of successes in the population divided by the number in the population. Okay, well, we can't calculate pi because maybe we can't get a census. So what we do is take a simple random sample. The simple random sample is going to have a bunch of successes and failures in it. We can calculate the proportion of successes in the sample. And remember, is p going to be the same as pi? Are we guaranteed that that's the case? No, of course not, right? And so p is the sample proportion, the way we calculate p, and we can calculate p because when we take a sample, we actually get to look at all those observations, or at least we should. So to get p, which is a statistic, the number of successes in the sample divided by the number in the sample. Okay? And so the idea is estimating pi. Remember we talked about there's more than one way to do estimation. Point estimation is the simple, easy way to do it, right? What's the point estimate for pi going to be?
0.14.
What's that? It could be 0.4, I guess. In some cases, maybe. But if pi is the parameter, the point estimate for pi is p. P could be 0.4, but it could also be 0.6 or 0.3. It does have to be between 0 and 1, though. Okay, so let me zoom out here. So this kind of says what I said before. Parameter pi we're interested in is the proportion of successes in the population. P is the proportion based on the sample. P is the point estimate for pi. But here the next step is, okay, well, point estimates are okay, but you really don't ever want to make any decisions based on a point estimate alone. And so what we may want to do is to do a confidence interval for pi. Okay, we did confidence intervals for mu, we've done confidence intervals for sigma. Now we're going to look at confidence intervals for proportions for pi. There's actually a lot of different formulas and methods out there to do confidence intervals for pi. And the one I'm going to show you is the one that's most commonly found in intro textbooks for courses like this. This is a pretty standard one that people do. And what you're really doing is just using a normal approximation here. But we'll call this the one sample z interval for pi. So remember, we're not estimating mu, we're estimating pi, where pi is the proportion of successes in the population. So the formula, it looks a lot like some of the ones we've done before, right? It's the point estimate plus or minus. What do you think this entire thing right here we're going to call the thing we add and subtract? Margin of error. That's exactly right. The thing you add and subtract is the margin of error. The margin of error is a critical value. And what type of critical value is it? Z. So when you get the critical values or the table values for this particular procedure, if you decide this is the procedure you're going to use, when you get the critical values, where are you going to find them? The very bottom of your t-table, because it's a z. Remember, a t with infinite degrees of freedom, that bottom row on your t-table is going to give you the z. So this will be like 1.96 or 1.6449, those kind of things. Okay? So all you do to get the margin of error, you take the z critical value times p times 1 minus p divided by n, square root, and there you go. Assumptions are pretty easy for this one. Again, something I want to point out and emphasize is every single one of these every different procedure that we're looking at or we're using has different assumptions. Some of them are pretty close and some of them aren't that close at all. Don't check the wrong assumptions. Don't just say, oh, n is bigger than 30, I must be okay. No, it doesn't always work that way. For this one, you've got to have a simple random sample, and the number of successes and failures both have to be at least 5. So maybe I should write that, because maybe it's not that clear. So both number of successes and failures need to be at least 5. Okay? Any questions about this? Okay, so next thing we'll do is take a look at some examples.